All right, we'll go ahead and get started. Welcome back, everyone from spring break. Hopefully you had a good time. We have with us today Enze Zhang, who is a postdoc here working with Ginny and Daniel Trugman. He got his bachelor's in geophysics from the University of Science and Technology of China, and then got his PhD in geosciences at the Chinese University of Hong Kong. And he's very interested in glacier mass balance, the variation of glacier terminus, and deep learning applications. And he's going to talk to us today about developing a deep learning based method to automate the delineation of glacier termini from remote sensing imagery. Take it away.
Thank you, Erin. Thank you for your kind introduction. I will share the screen. Okay, so good afternoon, everybody. Today, I'm going to talk about how to delineate glacier termini from big data based on deep learning. To start with, I would like to show this aerial photo. This is a photo of the Helheim Glacier, one of the largest glaciers in Greenland. And over here, we can see this is the glacier terminus. And our task is to extract the glacier terminus from remote sensing images. And why we care about glacier terminus? One reason is that glaciers in Greenland are retreating in dramatic rates. The left figure shows glacier retreat rates. This right circle means retreating and blue means advancing. We can see that most of the glaciers are retreating and in a quite dramatic rate. And to be more direct, this right figure shows the largest glacier, Jakob 7, has retreated more than 40 kilometers from 1851 to 2010. And by measuring the terminus variation, we can know how fast the glaciers are disappearing. And that's one of the objectives of measuring the glacier terminus. And also, glacier terminus is a good indicator of glacier dynamics. So glacier terminus is actually determined by two processes, the glacier movements and glacier calving. So as glacier move forwards to the ocean, the front will move forward as well. You can see the glacier move into this direction, the front will move as well. But at the front, the ice will calve from glacier and generate icebergs. Look at here, this is the large icebergs that generated from glaciers. So when the calving rate is larger than the flow rate, the glacier will retreat. So that makes a glacier a good indicator for glacier dynamics, because when glaciers are retreating, it means glaciers are losing mass faster. And additionally, a lot of studies have found the correlation between glacier retreat and acceleration thinning. It shows that glacier terminus might have strong influence on glacier dynamics. And one possible explanation is that the perturbation at the terminus at the S-ocean interaction might trigger glacier acceleration and inland thinning. So if we understand S-ocean interaction better, we can learn more about glacier dynamics and make more accurate projection about ice loss and also sea level rise in the future. But this kind of mechanisms is still unclear, and those kind of correlation, okay, here such correlation does not exist for all glaciers, meaning that these kind of mechanisms are complex. And to understand those mechanisms better, we need to do a detailed investigation. And that detailed investigation requires a fully comprehensive terminus dataset. So remote sensing data provides us the key observation of glacier terminus observation. So the data volume of remote sensing imagery in the polar regions has increased dramatically in the past 2 decades, which provides the foundation of a comprehensive investigation of the terminus variation. Here I list some of the operating satellite missions as example. So over here is the operating period. Over here is the number of images for a single glacier. This would To be noted that those are rough numbers. And for one glacier, if we sum all the satellites up, we will have around 1850 images, 18,050 images. And considering that Greenland has more than 300 major outlet glaciers, we will have more than 500,000 images in total. So therefore, it is impractical to manually delineate glacier terminus from those tremendous amount of images. And in this big data area, we need deep learning to help us to handle this difficulty. We need deep learning to automate the glacier front delineation. And how we can use deep learning to generate glacier terminus. The first step is to prepare the training data, which contains a training image and ground truth image. The training image is the remote sensing image, and the ground truth image a binary image where the glacier part is positive and non-glacial part is negative. So over here we can see those are glacier. And over here is the Esmelange. Sometimes it could become open water. So after preparing the training data set, we input the remote sensing image into the network. Over here is the input image, also the training image or remote sensing image. And over here is a diagram of deep learning network. And after the input image goes through this deep learning network, it will generate a segmented image, a black-white image. It is similar to the ground truth image, but it is not exactly the same. And then we will use the difference between the segmented image and the ground truth image, use the difference between them to update the parameter within the network. So that's what we call network training. Let the network learn from the training data set. So after the training process, after the network is well trained, so we give the network some new remote sensing images, and it can predict this black-white binary image, and we can generate or extract the glacier termini from them. So in recent years, there are several efforts using deep learning to generate glacier terminus, but most of them is in the method development stage, meaning they did not apply deep learning method to big data. So over here, those studies are still in the method development stage. Only one stage is close to use the big data. It's called Calvin. In this study, the author extracted around 20,000 termini at 66 glaciers. But how many images we have? We have more than 300,000 images at 295 glaciers. So the magnitude of the number of images is so different. And that is the truly big data. To apply deep learning to the big data, there will be several challenges from three aspects. One is from data collection, the other one is from diversity of the data set, and the last one is the quality control. For the data collection and quality control, we need them to be automatic, because if we do a simple things on so many images, it's going to be a problem. We don't want to spend months just to download data from a website, or spend another months to check the data quality. So we need those two processes to be automatic. And also, because the data set contains so many different situations, like different weather and illumination conditions, and different glacier orientation and fjord geometry. So because we cover so many images, it will contain all these different situations. So all these differences will increase the diversity of the data set, and we need to handle that. And we have two ways to handle that. One way is to to have a training data set that is comparably diverse to the whole data set. And the other one is we can normalize the diversity of the whole data set. So to decrease the complexity of the task. I will talk about this too later. So first, let's talk about how to automate the data collection. To solve the challenges from data collection, we use a platform called Google's Engine. So this is a powerful platform. It contains different remote sensing images and also other data sets, but here we only use the remote sensing imagery. And the amazing thing about this platform is that it can automate the data collection. So we just need to run some script and we can collect the images on this platform like 24/7. So we use all the eligible remote sensing data sets that covers the time span from 1984 to present. So I mean eligible, I need those data sets to cover the entire Greenland ice sheet. There are more other remote sensing imagery like Landsat 4 or Landsat 1, 2, 3, but those datasets does not cover the entire Greenland ice sheet, so I didn't use them. But for the 5 datasets that are listed here, they covers the entire Greenland ice sheet. So, all right. And to handle the diversity of the big data, we first need a training data set that is comparably diverse to the whole data set. So how to achieve this? We use TermPick as our training data set. The TermPick is the data set that collects all the valuable hand-picked terminus data set. It is developed by Sufi, one of our PhD students, and it contains more than 35,000 terminus from 278 glaciers. So the table here shows the studies that TermPick contains. It contains so many studies, and this data set is truly valuable for training the deep learning network because it can largely increase the diversity of our training set. But the terminus in TermPick are actually curves like this orange line. And to generate the binary ground truth images, we need to convert those polylines into polygons. To do so, we need to prepare a reference polygon for each glacier. So this green polygon is actually the reference polygon. So what we need to do is to replace this part with this green part with this orange part and generate this white polygon. That's what we need to do. Those 2 red points are the intersection between orange curve and the blue polygon. So after converting and manually check, we generate around 5,000 label polygons as our training data. But still, even though we have around 5,000 label images, there's still a large imbalance between the training image and the image we're going to predict. So it is the beautiful thing of deep learning. We can train the network, use limited amount of images, and use that network to predict more images. But when the imbalance is such big, like this, there's gonna be a problem. And to solve this problem, we have 2 solutions. One is we add more training data. So even though this TermPick derived training data covers a lot of situations, there will be some situations that are not covered by this data set. So we need to prepare additional training data that covers that specific situation. And the second solution is to normalize the whole dataset and to reduce the complexity of the task, so we can make it easier for deep learning network to predict where the terminus is. Right. And then I will talk about how to normalize the dataset. So here the normalization is conducted in two aspects. One is histogram and one is image size. First, let's look at the histogram. The top row here are the original image. This is original image, and normalized image. This is normalized image. This is another pair, but from different satellites. And the bottom are the corresponding histograms. So from this figure, we can see that images in different data sets over here and here, the value range are so different. So for example, for this one, the value range is from 0 to 2,500. But for this one, the value range is from 0 to 25,000. So, and also we can see that histogram pattern is so different. But after the normalization, all the histogram become a Gaussian distribution with identical standard deviation. So like this, and the image becomes similar. So that's what I mean by reduce the complexity of the task to make all the image look more similar to each other. So the network can learn the common feature among them more easily. And one more good thing about the histogram normalization is that it can increase the contrast and make the shadow area more clear. So for this image, as I will look at this image, it suffers from the shadow. So over here, we can barely see where the terminus is. But after we conduct the histogram normalization, the contrast of the image increases, and we can see the boundary in the shadow area more clear, and also the results are improved by the histogram normalization. Another key normalization is about the image size. So normalizing image size is important because all the glaciers have because originally all the glaciers has different size, but after we normalize the image size, it will have the similar size in the image. So because for some glacier, the width of the glacier may be like 2 kilometers, but for the other, it may just a few hundred meters. If we upsample the small glaciers to make it larger, then in image domain, it will be similar. So, and also before we input the network into, before we input the image into the network, we will split image into small patches with overlaps. So those overlaps will make the network make multiple prediction for the same place, and therefore it can generate more robust results. So if we upsample the small glaciers into larger one, it means that we can make more predictions for the small glacier, make the results of the small glaciers more robust. So that's why by normalizing the image size, we need to upsample the small glaciers, but not downsample the large glaciers. And these two figures shows the improvements after the normalization. So these top figures are original image, and the bottoms are upsample image. And also this left one is original, and the right one is after normalization. And we can see that after the normalization, the network can capture this small feature, which it can't originally. And after this normalization, data collection, we train a network and we use the well-trained network to make prediction. But there's one more important thing that we need to do is to do the quality control. Although deep learning is a powerful tool, it won't be perfect for all the images, but it will work for most of the data. So based on this, we develop an automated quality control method. And we first calculate the length, smoothness, and error change of the terminus. The error change here means the error between the two temporally closest termini. And after we calculate these, and for each of them, like the length, we will calculate the threshold based on the interquartile range based on this. So it is the mathematical method. It is purely based on the data distribution to find out where are the outliers. So this Q3 means 75th percentile, and the Q1 means 25th percentile. And then we use this two threshold to remove outliers to do the data quality control. All right. So after all this, we could generate Glacier terminus and calculate the time series of terminus variation. So over here, these small bars means the uncertainty, and the different color represents different remote sensing dataset. So these two glaciers have similar uncertainties, but the top glacier has large variation. So here is the value range, but the bottom one has a small variation. So for the top one, the uncertainty it looks small. It's just a relatively small. And here is another two examples. So to conclude this study, the deep learning can truly be beneficial in generating a fully comprehensive data in this big data area. So it can handle different scenarios, cover different situations, but when it really comes to the big data problem, we still need to handle the challenges either from data collection, quality control, or from the data diversity itself. So that's all for today's talk. I'm ready to take any questions or comments, suggestions. Thank you.
Thanks. That was a interesting talk. If you have any sorry about that, Ginny. I have a question to start with. Because I know the old way that this was done was kind of by hand picking the ends of the glacier and all that. For this kind of deep learning method, how many like glacier termini have you gone through and done this for? Like all of them already? Were you just showing us like 4 of the ones you have done?
Yeah, there's around 300 glaciers, and I have done 200 of them.
Okay.
Right, and it is still ongoing progress, and I found out there's around 10% still not working, and probably we need more training data. Right.
Gotcha.
And I saw Edward has a question.
I think he was clapping. He's in the office with me.
Hi, sorry I'm late. I had a student office hour visit, but That's a pretty big jump in the number that you've got complete from the last time we chatted. So that's awesome. Congrats.
Yeah. Right. I'm about to show you later.
Okay, sounds good.
So actually, the deep learning method has been developed from different studies, and it has shown that the deep learning has the spatial transferability and temporal transferability. It means that we train the network by using some image of certain glacier, and we can directly apply the network to another glacier. And also we train the network with a certain time period of images, like the images in 2013, it can be applied to 2020. So that's why the idea is that using a limited amount of training data to predict more and more images, right? But when the jump is too large, like from 5,000 to 500,000, then there will be some challenges, and tackling these challenges is the hardest part, actually.
I have another question. What's like the speed for your like sort of deep learning workflow from like start to finding the terminus?
Well, predicting won't take a lot of time. The time consuming part is the training. So when training the network, we usually take a week, depends on how large the training set is. If the training set keep growing, then we will need more and more training time, right? And it will grow up because we need covers some different situations. And usually, if we make single prediction, it will take several minutes. Yeah, it is pretty quick, but please be noted that we have around 300,000 images. So if we predict all of them, it still requires time. And beyond that, the post-processing, like the data quality control, we need to calculate the length, the smoothness, or the error change from the terminus. It also requires time, and sometimes it will take more time than just predicting.
Hey, Enze, I have a question for you. So I sort of joined the meeting in the middle, so I missed the first part. But when you showed that area change of certain glacier, it seems there's a trend. Can you show the slides again?
Yeah, sure.
I'm just wondering like what's happening there.
Okay.
Yeah,
here?
Yeah, that one, these ones.
Yeah, so
it doesn't look like seasonal, and it's sort of consistent among different like data.
You mean
so
over
what
here?
Are these? Yeah.
You mean over here those jumps?
Yeah.
Oh, that's thanks for asking. That's one of the big advantage of using this deep learning to apply to this big data, because we have the big data. We can largely increase the temporal resolution. So that's why we can find out those phenomena. This is called large carving event.
Okay.
So sometimes when the glacier is floating, and it will generate tabular icebergs. Like it's not a small iceberg. Is when the glacier generates small icebergs, the iceberg will flip or turn over or something. But when it generates a huge iceberg, it will directly come from the glacier and keep the surface at the top. Right. So that's why we have this dense time theory, and we can discover this kind of phenomenon. And from this time series, we can even directly count how many large calving event this glacier has been through in a certain time period.
But if it's an iceberg thing, shouldn't the area become smaller? Like, but I saw all the jumps are like positive.
Sorry. The positive means the area is decreasing.
Oh, okay.
It
Yeah,
means
that makes
glacier
sense.
is retreating. Sorry about
Okay. Thanks.
Thanks for your question. Yeah, about the deep learning other applications. So if
yeah, I'm just curious to see what other people's interests are, because it's sort of a new technology for me, and I can see the use in glaciology, but sometimes when you talk to other people who want to use it for different things, you get new ideas of how you might apply it in your own field. So I'm just curious if other people have been applying it in their own discipline, and what the possibilities are that maybe we could extend to glaciology and coastal change.
Yeah, and Eric, since you are a InStar expert, I recently I do have a question. So I've seen studies that use deep learning to remove the atmospheric delay in the intervals, right?
Yeah,
so I just want to know traditionally how we can remove the atmospheric delay.
Well, there are like lots of methods. One way apparently is to use other data sets like the meters data or that's on board or other like a satellite like data to do a weather model. And then you remove that weather model from your interferogram. But sometimes it works okay, sometimes it's not. That's one way. The other is like you do some kind of temporal smoothing. Or you estimate the atmospheric noise as part of the time series solution. That's another way of doing it. And I've seen people doing spectral analysis, like, the atmosphere is something like a red spectrum. So if you estimate that component from the interferogram, remove it. And also there are recent like machine learning methods to remove atmospheric noise while keeping the real signal.
Yeah. That's
but you have to define what's real first.
I think the idea is that if the real signal is temporally and spatially correlated, but for the atmospheric delay, it's just pure noise. It is random.
Well, atmospheric noise is not pure. Like it's not random noise. It's spatially correlated, and sometimes it's temporal correlated as well.
Okay, but when the time span is like 6 days. Or even longer, it still be correlated.
You mean temporally?
Yeah.
Yeah, it will. I mean, when you look at those GNSS studies, when they estimate the temporally correlated noise, usually they assume like random plus random, I mean white noise plus a spectrum that's sort of decays with frequency, which is also red spectrum in time. If you do a spectrogram, it'll show up. I mean, the noise is not just random noise. It is correlated, and actually, this kind of noise doesn't affect much on the velocity estimate. Like if you have a time series, you estimate this rate, it doesn't affect much on it, but it affects uncertainty of that rate.
Oh, okay.
Yeah.
Because sometimes when the deformation is small but steady over time, then it may be hard. It may be necessary. We need to remove the atmospheric delay, and it's hard to do so because the amplitude is small. Yeah,
well, the amplitude it matters in what kind of like wavelengths you're looking at. If you have a small amplitude or a very short like scale, then you'll be able to resolve it like with some stacking or time series analysis. But if it's a small amplitude or a large scale, it's going to be really hard because the noise spectrum of atmosphere is also increases with wavelengths. So
one more thing, do you think it is possible that we generate synthetic atmospheric delay?
Yeah, you can. I mean, I've done that before. You just produce a random noise and then scale it in spectral domain, and you transform it back, it looks like red noise. But
Okay.
but you can't simulate things like weather fronts or like events. Those are hard.
Yeah.
And also the, what do you call it? Those wiggles you see in the interferograms. It's from the gravitational waves. Like when the wind hits a mountain, it'll perturb the atmosphere and generate wiggles. Those are hard to simulate. Yeah.
Okay. Thanks for.
I myself actually have been working on something that's sort of related to machine learning, but I'm not an expert on that. So you might have some perspectives on it. The thing I did is I'm trying to, how to say, so we have this huge signal in Central Valley. Many of you guys probably already know it's subsiding at a very fast rate. But the thing that I'm trying to do is that, are we able to predict the deformation pattern, pattern just based on other records like GNSS? I sort of need to open the door. I'll come back in very shortly.
Sure.
Sorry.
No problem.
I don't really do anything with machine learning, but we had another talk in the discussion hour from a PhD student at Stanford who was using sort of like machine deep learning methods to do geophysical inversions of like electrical resistivity data. So that was another interesting application.
Sounds cool.
I don't know if that would relate to glaciers though.
We do all kinds of inversions for trying to measure or to understand the basal shear stress underneath the ice sheet where you can't actually do observations. So one thing I've thought that machine learning would be really valuable for is actually the boundary conditions of ice sheets, because the sort of, I mean, the rheology of ice is fairly well understood, and there are existing equations for modeling how ice deforms. But it's really the boundary conditions that are challenging, and there's no parameterization for them. There's no standard equation. And so that's sort of where Enze and Kevin are working at the ice-ocean boundary, but the other one is the ice-bed boundary. We don't have any like sliding law that's universal. And so using whatever observations we can to design these parameterizations is one avenue that I see for machine learning in glaciology, at least.
Hey, I'm back.
Keep going.
Can I continue? Like
yeah, sure.
Okay, so you know those kind of deformation patterns like in Central Valley subsiding or at a very fast rate, but we only have INSAR acquisitions over the recent, I don't know, like 20 years-ish or 30 years-ish. I'm thinking whether we could predict those kind of deformation patterns using other records like GNSS. So the way is that you input those as those records as how to say the prediction data it's using, and then you predict what it looks like in an interferogram. We have a time series over there that can be used sort of as the training data set, and then you can use later acquisitions and GNSS or other records as verification. If that works out well, that means you can sort of predict what the deformation sort of look like, even if you go back, I don't know, like 50 years, because you also have other data sets like well logs, right? So that's the thing I'm working on. It looks like that it's able to predict the pattern, but it's not able to generate, how to say, those very small details. It's a little bit hard because it's like point records that you're trying to use to predict the whole image. So I just kept adding layers, and
you should talk with Daniel, because that's exactly what Kevin Shianalin, who's like underneath me here, is trying to do for Glacier termini using what is it, Kevin, like XGBoost, I think is like so we're taking a time series and eliminating the last 3 years of data to use as verification of the method. But we're not there yet, but
XGBoost,
yeah, he's been helping to design it. So he might be helpful for what you're working on too.
Yeah, I'll write you guys emails once I have something to to show.
That's great.
Awesome. Do we have any more questions for Enze?
All right. Thank you all
Cool.
for listening.
Yep. Thanks for coming. See you guys next week.
Bye-bye.